Part 2. You'll notice that I converted each of my numbers to standard form, did the operation, and then converted them back to scientific notation. There is probably a better way, and we're going to learn about that today and Friday. On the first one, 2 times 10 to the 5th is 200,000 plus 600,000, 6 times 10 to the 5th, which gives me 800,000. I convert that back to scientific notation, which gives me 8 times 10 to the 5th power. On the next one, we get 4 and 1/10 times 10 to the 7th power times 2, which is 41 million times 2. I get 82 million. When I convert that back to scientific notation, I get 8 and 2/10 times 10 to the 7th power. On the third one, we have 1 and 5/10 times 10 to the 11th power times 3. We have 150 billion times 3, which gives me 450 billion. When I convert that to scientific notation, I get 4 and 5/10 times 10 to the 11th power. On the third question, we have 3 times 10 to the 3rd power squared. Or we could write that 2 different ways. We can go 3,000, which is 3 times 10 to the 3rd power squared, which is 3,000 times 3,000. Or we could square each term inside, 3 squared and 10 to the 3rd squared, which would give me 9 times 10 to the 6th power, because 3 times 2 is 6. Or if we did the 3,000 times 3,000, which gives us 9 million, we convert that to scientific notation, we still get 9 times 10 to the 6th power. On the last one, we have 2 scientific notation numbers, 9 times 10 to the 6th times 3 times 10 to the 6th. Well, commutative property of multiplication tells me that I can rearrange my factors. So I'm going to multiply the 9 times the 3, and I'm going to put the 10 times the 6 times the 10 times the 6. 9 times 3 is 27. When I do like bases, I add my exponents. I get 10 to the 12th power. But 27 is not going to be a number between 1 and 10. So I convert or move my decimal one place. Since I'm adding a decimal place, I'm increasing my exponent by 1. For each place I move, I only moved one place. So 12 plus 1 is a power of 13. So 2.7 or 2 and 7/10 times 10 to the 13th power. For our last problem, we have Jada trying to make a scale model of the Earth, distance from the Earth to Moon and from the Earth to the Sun. And we find out that she's going to set it on a desk or a dresser about a foot apart. It tells us that from Earth to the Moon is about 2 and 389 thousandths times 10 to the 5th meters, or miles, and from Earth to the Sun is about 9 and 296,000 times 10 to the 7th power miles. So I want to find out how many times farther it is to the Sun than it is to the Moon from the Earth. And then we're going to determine should the Sun be on the windowsill inside the same room, in her kitchen, which is down the hallway, or a city block away. So if I'm finding out how many times farther the Sun is than the Moon from the Earth, I'm going to divide those. I take, using my properties of multiplication and division, I'm going to divide the 9 and 296 thousandths by 2 and 389 thousandths. That's about 4 times. I should have used an approximation symbol here. Okay. And then I know how to divide exponents with like bases. I simply subtract my exponents. So 10 to the 7th divided by 10 to the 5th gives me 10 to the 2nd. Well, 10 squared is 100 times 4. So 400 times farther is the Sun than the Moon from the Earth. So Since the sun is about 400 times farther from the earth than the moon is, the sun would have to be 400 feet away from the earth model. Since the house or apartment is not likely to be 400 feet long, a block away would be about right. Consider the fact that 300 feet is the length of a football field. So, we will now be working on scientific notation, multiplication, and division.